Okay, let's first see a minimum spanning tree. Let's see a problem. For example, we want to network a collection of computers. We want to network them, and by linking some cables. It means by connecting different computers with some cables. So we can a graph problem. This is actually a graph problem. It means that the nodes are computers, and these cables or these links could be on directed edge of this between among the different nodes. They means we use some cables. Cables means links, and this is the distance among different computers. And the goal is to pick enough of these edges that nodes are connected. And it means, just now I say that a maintenance cost. So the distance may be a kind of maintenance, can represent a kind of maintenance cost. Because usually the distance means determines the length of the cable you need to install, you need to use, and it reflected in the edge's weight. So it means this is length means the edge's weight. So the goal is how could we find the cheapest possible network? It means we find the cheapest combination of these edges to connect all the nodes, and it means select the cheapest combination from this all of these candidate edges. So actually this is a graph problem. So let's see how to solve this. We can see that. Let's see the first property. Removing a cycle edge cannot disconnect a graph. So what does it mean? For example, if here is a circle, if we remove one edge, it will not disconnect A from this graph. Even here, this edge does not exist, and only this one, only these three. For example, you can, for example, here let's see this example. Here is a circle. Here is a cycle, and if we remove one edge of this cycle, we cannot disconnect F from the whole graph, because if we delete this one will connect F. If we delete this one will connect. If we delete this one will connect. So it means when there is a cycle, removing a cycle edge cannot disconnect a graph. So one immediate observation is that optimal set of edges cannot contain a cycle. So it means that for the optimal combination of the cheapest possible combination of cheapest network, it will not include a cycle. So when there is a cycle, it means that we can remove one edge from this cycle to reduce the cost. So we see that the solution must be connected and acyclic. Acyclic means there is no cycle. And undirected graphs of this kind are called trees. So this is a possible connection, or this is a possible network for this problem. It means we have select some edges from this graph to form a network. to form a solution for this problem. Okay, we can see that there's no circle in this solution. And for example, when there is a circle, for example here, a circle here, for example here, we can remove any edge from this circle, and it will not disconnect this graph. So it means that when this graph is connected, it means any node is from any node we can reach other nodes. So it means connected. So for a computer system, if we can connect to any nodes, it is a possible solution to this problem. So there may be different kind of trees, different trees for this problem. So this is a solution, and we may find another one. For example, we can remove this edge to here, or we can remove this edge to here, or we can remove this edge to here. We can construct different trees for this problem. So what is the one we want? Actually, the one we want is the minimum, is the tree with the minimum maintenance cost, because different edge has different maintenance cost. So we want to find the tree with the minimum maintenance cost. So we call this kind of tree minimum spending tree. So the formal definition for this problem is that the input is an undirected graph. For this graph, this is graph. V is the size of nodes and E is the size of edges. And for each edge, the weight of the maintenance cost is WE. And the output is a tree. The tree means V is the original V, but E is a subset of this one. Subset. And that minimizes the total weight, means minimize the total maintenance cost. So we have got the formal definition of this problem. So let's see how to solve this problem. Let's first see the Kurzkopf minimal spending tree algorithm. So it means that the main idea of this algorithm is that we can start with the empty graph. For example, giving you this graph, at first we remove all of this edge. At first give you an empty graph, and then select edges. We select edges from all the counted edges one by one. To following the rules, we add the next latest edge. It means every time we select the latest edge, that doesn't produce a cycle. It means that we will construct the tree edge by edge, and apart from taking care to avoid cycles. So it means that, for example, when you have put this, for example, if you have selected this one and this one, and okay, for example, when you have selected this one and this one, and for example, if the next is AC, then it will produce a cycle. So it means this edge cannot be selected because it will produce a cycle. So it means that every time you select the lightest edge, means the cheapest edge, and it will not produce a cycle. If it will produce a cycle, it will be ignored. So this is a greedy algorithm. You can see that every time it only focuses on the short-term benefit or short-term advantage. Every decision it makes is the one with the most obvious immediate advantage. So it means that we will sort the edge in increasing order. in increasing order of their weights. For example, BC is the edge with the minimum maintenance cost. So then we will check edge by edge to add them one by one to this graph. And if it will produce, for example, at first we select BC, and then we select CD is the next cheapest, and then we select BD. But when we are putting BD, we find that it produces a cycle. So since it has produced a cycle, we will ignore this edge, and then we put CF, and then we select DF. When we are putting DF, we found that DF will introduce a cycle, so we will ignore DF, and then we put EF, and then we put AD, we put AB. When we are putting AD, we find we introduce another cycle from this one. So we ignore this AB, and then we put CE. When we are putting CE will introduce a cycle, so we ignore CE. And finally AC will introduce another cycle, so we ignore AC. So we have built a minimal spanning tree. So is this optimal solution? So let's try to prove. We can prove that by studying cut property.